Hello students. Today we begin our journey into the first chapter of class 10 mathematics, which is real numbers. At the first, the name may sound very simple. After all, you have been working with the numbers since your early classes, natural numbers, whole numbers, integers and fractions. But have you ever stopped to think what exactly are the real numbers and why are they so important? Real numbers are not just numbers we use for calculations. They form the very foundation of the mathematics, whether it is measuring distance, calculating speed, or handling money, or even designing technology. Everything depends on real numbers. So in this chapter, we will go deeper into concepts you have already seen, like factors, multiples, and explore powerful ideas such as the fundamental of factorization and how to calculate the HCF and the LCM. So in this chapter, we are going to talk about the fundamental theorem of the arithmetic, which helps us to understand how numbers are related. We'll also learn about the prime factorization, HCF and LCM, and discover an interesting property about the numbers. We will further look into the concept of irrational number in this chapter and try to prove that how a particular number can be proved to be irrational by using the contradiction mechanism. And we are going to cover all the examples which are there within the NCRT book along with all the NCRT exercise. The focus is to first brief the concept, so that concept is being acquainted with the students, and then definitely help them with the solutions to the basic problems and the examples. So with this, let's just start the chapter. Okay. So key topics that we're going to cover today as a part of this chapter is we'll understand the concept of fundamental theorem of arithmetic. Uh, we are going to spend some time in understanding and figuring out irrational numbers. We have studied about that in class 9. We are going to do a bit deep and try to prove that how a particular number can be proved to be irrational with the help of contradiction mechanism. And then we are going to look at all the questions and the solution for the NCRT problems. So we'll start our discussion by first slide by looking at the fundamental theorem of arithmetic. Okay, so we are going to first understand the concept of the fundamental theorem of arithmetic. So every composite number can be expressed as a product of prime number. What does this mean? So if we have a number, what we have to do, we have to break that number in the form of prime number. So which means that we have to break that number so that each number can be presented at a as a product of the prime number. So this theorem says that every composite number can be expressed as the product of prime number. This factorization is unique. So which means that a particular number, when we create the prime factorization, that that would be unique. It cannot be something which can be applicable to any other number. So a particular number will be having a unique set of the factors which can be shown as the product of the prime numbers. Prime numbers are what? A numbers having only two factors, which are what are those? So one and itself. So which means that we are talking about a set of numbers wherein there is no common factor. The factor is either the number itself or the one. For example, 2, 3, 5, 7, 11. So these are like prime numbers. For example, if we say 2, so 2 means what? A number itself, which is 2 and then 1. So 2 into 1, 2. That is the only factor that is available for that number. Likewise, for 3, we only have two factors, which is the number itself and the 1, which is 3 into 1. So prime numbers are the numbers which are having only two factors, the 1 and the number itself. And then we have a composite number. So what are the composite numbers? So composite numbers will have more than two factors. For example, if you look at the 4, so then 4 would be having one factor as 4 into 1, another factor as 2 into 2. So which means that the number is having more than two factors, which is number itself and 1. Then it has, so typically it has three factors here. So 2 into 4 into 1, which is 4, 1 and 2. So three factors are there, 2, 4 and 1, which means that this number is a composite number because it has three factors, which is in contradiction to a prime number which only has two factors. Likewise, for 6, we have 2, 3, 6 and 1. These are the factors for 6, and because it has more than two factors, which is number itself and the 1, and hence this is a composite number. So thumb rule is that composite number can be broken down into product of the prime number. So prime factorization is a concept whereby we break a number into the multiplication of the prime number. For example, if we look at 60 as one of the number, which is the composite number. So what we have done, we have created the factor for that particular number, and we are saying that 2 times 2, which is that's 2 multiplied by 2, which is 4, 1 times 3, 4 into 3, 12, and then 1 time 5, which is the multiply by 5 as well. So which means that 4 into 3, 12 into 5, 60. So this 60 is the prime factorization of a particular number, and 60 can be represented as a product of the prime number, which is 2 into 2 into 3 into 5. This is what fundamental theorem of arithmetic says. It says that a particular composite number can be expressed as a product of the prime number. So when we look at this concept, this simply says that this is a concept whereby our particular number can be expressed as a product of the prime number. So this is the concept of fundamental theorem of arithmetic. So with this, we'll move to the next slide and understand more details about it. Okay, so continuing with the fundamental theorem of arithmetic, we are going to talk about another property of this theorem, which is the uniqueness property. And what does this uniqueness property means in the context of fundamental theorem? It says that number has only one unique prime factorization. So when we're talking about a particular number, that number can be presented as the uniqueness of the prime set of the prime numbers, which can be composite number can be broken into a unique set of the prime numbers. And for example, 180, if we're talking about, then it has a factor of 2 square 2 multiplied by 3 square 2 multiplied by 5. So this is a unique combination of the prime number, which for which a particular number can be represented. And likewise, any composite number will have a unique combination of the prime number, and that unique combination is the unique for that particular composite number. So when we use this combination, so a particular number then can be represented as the product of the unique set of prime numbers. So no other combination of prime can represent 180 apart from the one which we have shown here. Uh, and how we have to do the factorization using the how we have to do the factorization using the prime factorization method is, first we have to divide the number by the smallest prime. We'll start with the 2. We'll figure out whether the divisibility rule which is applicable to 2 is applicable to that number or not. If not, then we'll start with the 3 and with 5 and with the 7, and we'll move on. And we'll start with the smallest prime number. We'll continue the division until the quotient is 1. So once we have achieved the quotient 1, which means that we have done the prime factorization of that particular number. So if you look at the example here, which is 180, so 180 can be simply be represented as the product of 2 multiplied by 2 multiplied by 2 multiplied by 3 multiplied by 3 and then further multiply by 5. So what does this mean? This means that a particular number can be broken down into the product of the prime number, and we'll continue this exercise till we have achieved the quotient which is 1. And once we apply this, we can use the outcome of this prime factorization to derive two things. What are those two things? We can find the LCM, and how we find the LCM? We'll take the common prime with the smallest power. So which means that if we have a set of two number and we do the prime factorization of those two numbers, then how we have to find the HCF? We have to identify the common multiple, and we are going to use the smallest power for that common multiple to derive the HCF. But for LCM, what we'll take? We'll take all the prime number with the highest power. So which means that if we have a two number and thus those two number has a different prime factorization, then what we how we have to find the LCM? We will first understand the total prime numbers in that particular set of the numbers, and then we are going to use the highest power. We're going to talk about this in detail in the upcoming slides so that this concept become more clear, that how we have to derive the HCF and the LCM by using the prime factorization method. So we'll move to the next slide. Okay, now we are going to understand the concept of fundamental theorem of arithmetic with the help of a quick example here. And what we are saying that we are taking a number here, and considering a number, the number is 4n, where n is a natural number. And what we are trying to say is we have to check whether there is any value for which 4n ends with the digit 0. Okay, now we have to use our understanding of the divisibility that we have learned in the classes 8th or 7th, whereby we understand the divisibility rule. Now, when we talk about the divisibility rule, condition for a number to end with the 0 is a number end with 0 if it is divisible by both 2 and 5. Why we are saying both? Because a number, if it is divisible by 5, it can also have a number which ends with the 5, not necessarily a number which will be having the 0 when it is divisible by 5, because 35 is also divisible by 5. So, which means that a number ending with 5 is also divisible by 5. But when we're talking about a number which needs to be divisible by 10, then it has to end with the 0. And to end with a 0, a number has to be divisible by both 2 and 5. This is the first condition that we have to check. So our question is that we have a number 4n, and then we have been asked to check whether there is any value of n for which 4n ends with the digit 0. So which means that if 4n end with the digit 0, then it has to have this condition to be satisfied. So which means that the number needs to be divisible by both 2 and 5. This is the first condition. So the number must contain both the factor 2 and 5, which means that number must be divisible by both 2 and 5. This is the very important condition that needs to be first looked into before we can actually start to solve the problem. Step 2, what we have to do? We have to do the prime factorization of 4 to the power of n. So when we say 4, we can express the 4 into form of the prime factorization, which is 2 into 2, because when we understand that when we have to solve a particular number, then we have to start with the smallest prime number. So what we'll do, we will say 2 into 2, which is my 2 square. So 4n can easily be represented as 2 square to the power n. So which means that 2 to the power 2n. So 4n contains only factor 2. So with this, we conclude that 4n only contains factor 2, and it is not having a factor 5, which is essential ingredient for a number to be divisible by 10. So check for 5. So we will check that 4n is equal to 2 to the power 2n. So there is no factor of 5 present here. So what is the final conclusion? Since 4n does not contain factor 5, it cannot be divisible by 10. Therefore, there is no natural number for n for which 4n ends with the 0. So this is how we have to prove the particular number and confirm whether it is divisible by 10 or for that matter any other number. So first we have to understand the divisibility rule. We have to apply that divisibility rule, break the number into the prime factorization method, and confirm whether divisibility rule is being applied and is successfully being applicable for that particular number. And if not, then definitely we can say that that particular number is not divisible by a particular factor, and in this case our factor is 10. Now we have another example. Find the HCF and the LCM of 6 and 20 by the prime factorization method. So in the previous slide, we learned that how we have to apply the prime factorization method to break a particular composite number. So in this, our two numbers are 6 and 20, and these both are composite number because it has factor which is more than 2. What are those two factors? The number itself and the 1. So if we talk about 6, then 6 is having 2 and 3, and 20 is having 2 to the power of 2 and 5. So which means that it has a factor which is 2 into 3 and then 1 itself, and then it has a factor 2 into 2 into 5 into 1. So all these are the prime factor for a particular number. So what we have to do, we have to first break that particular composite number and with the help of the prime factorization method. Now step 2, we have to find the HCF. So what we said that to find the HCF, what we have to do? Common prime factor with the smallest power. This is the rule that we have to apply. Common prime factor with smallest power. So what is the common prime factor here? 2. This is common here. 2 square. This is the common. So first we have to identify the common factor. So common factor is 2 and 2. 3 is unique for 6 and 5 is unique for 20. So which means that 3 and 5 are not common. So common factor is 2. Now what we have to do understand, we have to apply the lowest power. So what is the lowest power here? Lowest power is 1. Okay. So 2 with the minimum power is 1. Therefore HCF is 2. This is a particular way, this is a method through which we have to find the HCF of a particular set of numbers. Then we have to find the LCM. And what is the formula for LCM? all prime factors with the highest power. Now we'll talk about all prime factors. So 2 is factor here, 2 is also factor here. This is common factor, but highest power is 2. So we'll take 2 multiplied by 2. Then formula is all prime factors. So which means that we have a 3 as a prime factor in the 6, and then we have 5 as a prime factor in 20. So we'll take those two as well. So we have taken 3 and then we have taken 5 as well. So we have taken both the numbers. So what we have to do, we have to multiply the all the numbers that we have taken, all the factors which are there. So all prime factor with the highest power is 2 to the power of 2 multiplied by 3 multiplied by 5, which means 60. So 60 is my LCM. Now what we'll do, we'll verify whether our calculations is correct or not by using a very important concept, which is the HCF into LCM is equal to product of a two number. This is a theorem, or you can say that this is the fundamental theorem of arithmetic by which we can apply this. HCF into LCM is equal to product of two number. So our HCF was 2, LCM was 60. So 2 multiplied by 60 is 120. And then we'll verify it whether the product of our two numbers is also 60 or not. So our two numbers were 6 and 20. When we multiply 6 and 20, we'll get 120. So which means that whatever calculation we have done, it is correct, and our HCF and LCM are also correct. So with this, we'll move to the next slide. So we have another example to demonstrate the concept of fundamental theorem of arithmetic here. So what this example says to us, find the HCF of 96 and 404 by prime factorization method. Once we have to find that method, then we also have to find the LCM. So again, we'll follow the same concept. We'll do the prime factorization of 96 and 404, sorry. So for 96, we have create a factorization table, and we are saying that 2 multiplied by 2 multiplied by 2 multiplied by 2 multiplied by 2, which means that 2 to the power of 5 multiplied by 3 is the prime factorization of 96. And then for 401, we have 2 to the power of 2 multiplied by 101. This is the prime factorization of 404. Now to find the HCF, we have to first find the common factor here. So common factor is 2 and the smallest power is 2. So 2 to the power of 2 is the HCF that we're going to get, because the common factor is 2, and between 2 to the power of 5 and 2 to the power of 2, we have common power of 2, 2 to the power of 2 as the number which will represent the HCF. Now, once we have find the HCF, either we can use the simple method that we used in the last slide by adopting the fact that we'll take the highest power of the factors that are available. We can use that as well, but we can also use the formula here. So what we have, the formula we have to use, because we know that HCF into LCM is equal to product of two number. So if we have to find the LCM, what we have to do, the product of two number would be divided by the HCF. This is the method that we can use to derive the LCM. So product of the two number is 96 into 404, and the HCF that we have derived, which is 4 here. So when we'll solve this, we'll get answer 9696, and 9696 is the LCM. Now, largely we are using the concept of the formula, and we can verify it again. But since we are using this formula, the verification turns out to be true only. So we'll verify it. HCF into LCM is the product of two number. So we have 4 as the HCF, we have 9696 as the LCM. When we multiply, we get 38784. Likewise, if we verify it by two numbers, so we have 96 and 44 as the two number. When we multiply these two number, our answer is 38784. Now, when we apply this logic and when we apply this rule that LCM into HCF is the product of two number, this hold very good when we are talking about two number. But the moment we have more than two numbers, then definitely we are going to adopt the same method that we have adopted in the previous slide, whereby we have to find the HCF by taking the common factor with the lowest power, and we have to find the LCM with the factors with the highest power. So example, we have to find the HCF LCM of three numbers here, 6, 72 and 120. We'll do the prime factorization of 6, 72 and 120. And then we have to find the HCF. So we have to look at the number. So we have the common factor as 2, which is there in all the three. Common factor is 3 is also there, which is all in 3. The smallest power is, we have these 1, 2 and 1, 3. So which means that 2 multiplied by 3, which is equal to 6, is the HCF for that particular three set of numbers. So we'll move to the next slide and look at how we have to calculate the LCM. Okay, so continuing the previous example that we looked into, we are going to find the LCM now. So take all the prime number with the highest power. So LCM was 2 to the power of 3, which is the highest power for one number, 3 to the power 2, which is the highest power for any other number, and then 5. So when we multiply this 3, we'll get the 360 as the LCM. Now, important tip is that HCF is equal to smallest power of the common prime, and LCM is the highest power of all the prime. This is the method that we have to adopt. So we have to remember this very, very clearly. HCF is equal to smallest power of common prime. LCM is equal to the highest power of all primes. Now we have created the we have a solution the exercise for this particular theorem, which is exercise 1.1. So we have to express 140, 156, 3825, 5005, and 7429 as the prime factorization. So 140, when we do the prime factorization, our answer is 2 to the power of 2 into 5 into 7. 156, when we do the prime factorization, this is the answer. And likewise for 3825, when we do the prime factorization, we have an answer 3 to the power 2 into 5 to the power 2 into 7. Likewise 55005, the answer is 5 into 7 into 11 into 13. And for 7429, we have 17 as one of the prime factor, then we have 19 as one of the prime factor, and then we have 23 as one of the prime factor. So this is how we have to break a particular number into the product of the prime number. We'll move to the next slide and look at other questions for exercise 1.1. Okay, so now we're going to talk about another question, which is we have to find the LCM and HCF of the following pair of the integers. And then we have to verify also whether LCM into HCF is equal to product of two numbers. So we have given a two set of number 26 and 91, another set 510 and 92, and another set 336 and 54. So for first number, which is 26 and 91, the prime factorization of 26 is 2 into 13. For 91 is 291 into 7 into 13. We look at for the common factor here. Common factor is 13, and 13 the lowest power is 13 to the power of 1. So hence our HCF is equal to 13. When we look at the LCM, we have to look at the prime factor with the highest power, factor with the highest power. So 13 multiplied by 7 multiplied by 2. This is the LCM. We have 182 as the LCM, and as a verification we'll multiply the LCM with the HCM and we'll verify whether this is equal to product of two number, and if answer is yes, then our solution has been verified. Then we have another set of number 510 and 92. Prime factorization of 510 is 2 into 3 into 5 into 17, and 92 is 2 to the power of 2 and 23. If we look at the HCF here, so we have 2 as the common factor, and then the single power is 2, lowest power is 2 to the power of 1, hence our HCF is 2. Then we have to find the LCM. What the rule says, we have to take the factors with the highest power. So 2 to the power of 2. Then we have 3, 5, 17 and 23. So 3, 5, 17 and 23. We multiply all together to get the final LCM, which is 46980. And then we'll apply our logic of LCM into HCM is the product of two number. And if it is equal, then means that our answer is verified. We'll solve the third question in the next slide. Third question is 336 into 54. And when we look at this, we'll again break down 336 into 2 to the power of 4 into 3 into 7. 54 is 2 into 3 to the power of 3. When we look at the lowest number, so 2 is the common factor and the lowest power is 1. And when we look at the common factor, 3 is the common factor with lowest power of 1. So 2 into 3 is equal to 6, which is the HCF. We'll find the LCM. So highest power of 2 is 2 to the power of 4, highest power of 3 is 3 to the power of 3, and then the remaining number is another factor is 7. So we'll multiply this together to get 3024 as the LCM, and then we'll also verify the same. And then we'll come to the next example. Find the LCM and the HCF of the following integers by applying the prime factorization: 12, 15, 21, 17, 23, 29, 8, 9, and 25. So we'll again do the prime factorization the way we have done for the early example. Apply the same logic to derive the HCF and then the LCM. So we'll move to the next slide then. So for previous example, HCF is 3, and then we'll apply the same logic to derive the LCM. Likewise for number 17, 23 and 29, since these are all my prime numbers. This is most important. So in case of the prime numbers where we do not have any common factor, then our HCF is by default 1, because we know that for prime number the factors are either the number themselves or the 1. So definitely if the number themselves cannot be the common factor will then become 1. So HCF in this case is 1, and then LCM is simply the multiplication of all three numbers together. If the numbers are prime, this is simple method that we have to follow. We have to simply look at it, apply the HCF as 1. This is very, very important if numbers are prime. For prime, HCF is always be 1, will always be 1, and the LCM is equal to the product of all the numbers. Next, we'll go to an example 8, 9, and 25. We do the factorization. We'll move to the next slide to look at the rest of the solution for this particular problem. Okay, so in this also HCF is 1, though the number are composite, but still we have HCF 1 because there is no common factor. So wherever where there is no common factor for a particular set of number, then HCF by default would become 1. And then LCM would apply the same logic, which is the factor with the highest power. We multiply them together to get the LCM. Now another question, given that HCF of 306 and 657 is 9, we have to file the LCM. So we have to apply that formula. HCF into LCM is equal to product of two number. We have to find the LCM. That is what we'll do. We'll multiply the product of two number and divide by the HCF. So our two number is 306 multiplied by 657, and then we'll divide by 9 to get the final answer of 222 And then we can do the quick verification by doing the logic of HCF into LCM is equal to product of two number to verify whether our answer is correct or not. So we'll move to the next slide. Okay. Now another question here. I think this is in line with what we discussed in the example that whether 4 to power of n can have any number with the digit 0. I think we are going to apply the same logic in this case as well. So what we have to do, we have to check whether the 6 to power of the n ends with the digit 0 for any natural number n. So again we have to apply the same logic. So step 1, the condition for a number to end with the 0. A number ends with 0 if it is divisible by 10, and divisibility of 10 is it has to be divisible by both 2 and 5. So number must contain both 2 and 5 to be divisible by 10. So when we do the prime factorization of 6, we say that 6 can be shown as a product of 2 into 3, and the 6 to power of n can be shown as the product of 2 into 3 to the power of n, which means that 2n into 3n. So 6n can be represented as 2n into 3n. It contains factors 2 and 3 only, and there is no factor 5. So if there is no factor 5, which means that it will not have any number which will be divisible by, which is divisible by 10 or digit 0. So 6n does not contain factor 5. It cannot be divisible by 10, and hence there is no natural number for n for which 6 to the power of n end with 0. This is very simple thing, provided we understand the concept of divisibility and we understand how to apply that. So this is a simple step method, and I request students to please follow this method, this mechanism only. You have to show each step to get the maximum number. So if this question comes, we have to first, step 1 is we have to check the condition for number to end with the 0. Step 2 is we have to do the prime factorization of that number, and step 3 we have to check whether both the factors, which is 2 and 5, is being available in that particular number or not. If not, then definitely this number is not divisible by 10. Next, we have a question. We have 7 into 11 into 13 plus 13, and these now we have to prove that these are composite numbers. So we'll go with the first number and we look at the solution in the next slide. Okay. Now we have a number here, 7 into 11 into 13 into 13. So what we have done for simplicity purpose, we have taken 13 as common here. So if we taken 13 as common here, then we have 7 into 11, and then we have plus 1. So then what we have to do, 7 into 11 is 77, 77 plus 1 is 70. So 13 into 78 is the product that we are going to have. So we know that 13 is a prime number. This is something which is known to us. But we know that 78 is not a prime number, and hence it can be broken down into set of the prime factor. So which we did 2 into 3 into 13 when we break it down. And then we can say that 13 into 78 can be represented as 13 multiplied by 2 multiplied by 3 multiplied by 13. So which means that this is a product of the prime number which is more than the two factors, and if a number is having more than two factors, then it is a composite number. So we know that for prime numbers it will only have two factors, which is 1 and the number itself. But in this case of 78, we in this case of 13 to 78, which is the number, we have multiple factors, which is we have 2 as a factor, 3 as a factor, 13 as a factor, and then we also have a 1 and then number itself as a factor. So which means that this is a composite number. Likewise, for the next example, 7 into 6 into 5 into 4 into 3 into 1 plus 5. So this is largely a factorial representation, though it is a kind of a bit high for this class. So factorial means that when we have a series whereby number can be multiplied by a number which is in the reducing sequence. So like 7 into 6 into 5 into 4 into 3 into 1 is 7 factorial. If it is 5 factorial, it would be 5 into 4 into 3 into 2 into 1. So if we just try to solve this 7 into 6 into 5 into 4 into 3 into 1, it is 5040, and then we add 5 to it, we have a number 5045. Now, when we break this number, it has a set of two number 5 into 1009. So again, it is having the factor which is more than two factor because 5 is one factor, 1009 is one factor, then we have 1 as a factor, and then we also have 5045 as a factor. So which means that factor is more than 2. So since it can express as a product of two number, and hence a composite number is it has more than two factors. So this is a way we have to prove that set of number is composite. Now we have another question here. This is a circular path around a sports field, and Sonia takes 18 minutes to drive one round of the field, while Ravi takes 12 minutes to do the same. Suppose they both start at the same point at the same time and they go in the same direction. After how many minutes they will start? They will meet again the starting point. So we'll look at the concept here, and then we'll also look at the solution. We'll move to the next slide. Okay, so in the problem that we have is we have to apply the logic of LCM here, because this is a situation wherein a repetition is going to happen. And repetition is largely being happen when we have lowest common multiple, when a particular multiple rounds would be completed. So in this case, Sonia completes the whole number of rounds. Ravi also complete the whole number of rounds before they can meet together, because then they have to complete the minimum number of rounds before they can meet together, and hence we have to find LCM in this particular case. So when we apply the logic of calculate the LCM, we'll do the prime factorization for 18 and 12, and we'll calculate the LCM. The LCM is 36, so which means that they will both meet after 36 minutes. So we'll move to the next slide then. Okay, so now we're going to talk about another important concept in this chapter, which is revisiting the irrational number. So we are going to understand what is the concept of irrational number, though we have talked about it in detail in the class 9th. So we'll again revisit what is the irrational number. A number which cannot be represented in the form of p by q, it can be is treated as an irrational number. So which means that the number cannot be expressed in form of p by q, and the number is not has a non-terminating and non-repeating decimal expression. For example, root 2 n. So if we have to talk about the important properties of the irrational number, we are talking about that sum of the rational and irrational number is always irrational. Product of a non-zero rational number and irrational number is always irrational. And if p is a prime, then its square root is irrational. So which means that three properties are there. Sum of a rational and irrational is always irrational. Product of a rational number, which means that number which is can be expressed in form of p by q, and the irrational number, it is always irrational. And most importantly, the if there is a number which is prime number, then its square root is always irrational. This is very important. So square root of prime number is always irrational. So we have a theorem, let p be any prime number if p divides square of a. So we have a number p, and then we have a number a, and if p divides square of a number a, then p also divides that number itself. So where p divides a, where a is the positive integers. So we have to prove that root 2 is irrational, and this is a very important theorem, you can say, that how we have to prove root 2 is irrational. Now we are going to use the contradiction logic here. So instead of proving root 2 as irrational, we will first assume let root 2 is rational. So assume root 2 is rational, and thus if root is irrational, then we can present root 2 in the form of p by q. Here said that p by q are the co-prime integers. So when we're talking about rational number, we have to be make very much sure that the relationship between p and q is such that p and q are co-primes. So which means that they do not have any common factor apart from 1. So example 2 and 3, 5 and 7, 13 and 17, 17 and 19, all these are set of prime numbers, and when we look at these are co-prime because they only have 1 as a common factor. So step 2, what we'll do, we say that let p by q is root 2, and what we are saying on squaring both the sides. So on squaring both the sides, we are saying that p square by q square becomes 2, and then we'll multiply 2 with the q square, then we have the 2 q square is equal to p square. This is simple. So here what we are saying that 2q square is a multiple of 2. So which because it has a 2 here, so which means that q square is a multiple of 2. And hence p square is an even number because 2q square is equal to p square, and p square is having q square is having a multiple of 2. So any number which has a multiple of 2, that number becomes the even number. Therefore, p is also an even number because p square is equal to 2q square. So we assume that. So what we are then saying that if our p is an even number, then we can put p is equal to 2x. Because even number can be presented in form of 2x, where x is an integer. And then what we'll do, we'll substitute p with the number 2x here. So then we are saying that 2q square is equal to p, which is being replaced by 2x, and square of it, we have 4x square. So q square, what we do then, we reduced that number 2 from here, and then 4 we reduced to 2. So we are saying that q square is equal to 2 into 2, and q square is an even number. Therefore, q is also even. So what we are then saying there is that if we have a number 2q square, and then 2q square is equal to 4x square, so which means that q square is also a even number, because 4x square is an even number, and hence q is also an even number. So hence p and q are even number, and they have 2 as a common multiple. So the moment we say that they have a common multiple 2, which means that p and q are not co-prime, because in the co-prime we can only have 1 as the common factor, but in this case we have 2 as the common multiple. So which means that our contradiction that p by q is root 2 is p by q is contradictory, because p by q number can only have co-prime number, and in this case we have proved that it has 2 has the common multiple. So which means that they are not co-prime, which means that root 2 is not equal to p by q, and if root 2 is not equal to p by q, then it is an irrational. So again, I'm trying to explain here in one more way, is that we have to make sure that instead of proving the number as the irrational, we have to assume as to be rational, and then we can prove that the number by solving it, that number is not rational because it contradicts the property of the co-prime. And once we prove that, then we can say that that particular number is itself a irrational number. And then we are going to talk about this in more detail in the examples, as well as the in the exercise that we are going to have. Thus, root 2 is irrational number by contradiction method. So we'll move to the next slide. Okay, now we are going to prove that root 3 is irrational. So we'll apply the same logic that we applied to prove whether root 2 is irrational or not. So what we are going to say then, we are going to again assume the same method. We'll prove root 3 is irrational using the contradiction method. Let us assume root 3 is rational number. Again, when we are talking about root 3 is rational number, then we are saying that it can be represented in the form of p and q, where p and q are both co-prime. Now we are saying that root 3 is equal to p by q, and what we have done, we have multiplied q with the root 3, so we are saying root 3 q is equal to p. Take the square of both the sides. So root 3 becomes 3, q becomes q square, and p becomes p square. Because 3 is a prime number that divides p square, so 3 divides p. So this is the theorem that we discussed in the slide of irrational number, wherein if a particular number is the square of a particular number is divisible by a particular number, then the number itself is divisible by that number. So in this case, what we are saying that 3 is a number that is divisible, divides p square, right? Then 3 divides the p as well. So 3 is the factor of p. So 3q square is equal to p square, which means q square is equal to p square by 3. And then this means that 3 is a prime number that divides p square, and hence it will divide p. Therefore, p is a number that divides q. Now we'll assume that p is equal to 3a. In earlier example, we assumed that p is equal to 2x, because that number was even number. Now in this case, we have to assume p is equal to 3a here. So we are saying that 3q square is equal to uh, p, which is represented by the 3a. We are saying that p is equal to 3a here. So we have 3a square. 3q square is equal to 9a square. So we reduce 3 with the 9 here. So we have q square is equal to 3a square. And then we have q square divided by 3 is equal to a square. So which means that 3 is a factor of q as well. So 3 is the factor of p, and 3 is the factor of q. So when we are saying that 3 is the factor of both p and q, which means that it contradicts to the assumption of rational number, because in rational number has to be co-prime. But in this case, we have a factor which is more than one factor, which is apart from 1, we have another factor which is 3. So from the equation 1 and 2, we conclude that 3 is the factor of P and 3 is the factor of Q. 3 is the factor of both P and Q, and this leads to the contradiction to our assumption that P and Q are co. So whenever we are getting these kind of question wherein we have to prove the number to be a irrational, we have to go with the contradiction theorem. We have to first assume that number is rational number, and then we have to ensure that our assumption is wrong by proving that that particular number is having more than one common multiple, which contradicts to the assumption of the fact that it is a rational number, because in the rational number a number only have one as a common multiple or common factors with respect to the p by q. But in this case, we have more than one common multiple or factor, and then this case, in this particular case, it is being proved that this number is irrational. Now for rest of the question, whenever we are going to have root 2, root 3, root 5, we have to assume and use the property of the fact that square root of a prime number is irrational. You have to use that property. I mean, in the many problems where we're going to have the multiple use, we cannot going to prove every time unless and until explicitly it has been asked that we have to prove a particular prime number to be irrational. But if we are going to have multiple numbers in which what particular prime number is being used and it is having a square root, then we have to apply the logic of the fact that square root of a prime number is always irrational. So we'll move to the next slide. Okay, so in this slide, we are going to talk about example 2 here. So example 2 is what? Show that 5 minus root 3 is irrational. Now, we are going to not use and explain that root 3 is irrational again by applying the logic that we used to express in the previous example. Here, we are going to use the property that square root of a prime number is irrational. So we'll use the contradiction method here, that 5 minus root 3 is irrational here. So let us assume 5 minus root 3 is rational number, which can be expressed in the form of the P and Q, and where P and Q are the co-prime. So we are saying 5 minus root 3 is equal to P by Q. Add root 3 to both the side. 5 minus root 3 plus root 3 becomes 5, and P by Q is equal plus root 3 becomes 5. So this is the first thing. So typically our attempt is that we have to isolate the root here, which means that we have to make an equation such that we have to get root 3 or relevant root in the one side, and rest of the equation should be on the another side. So in this case, 5q minus p upon q is equal to root 3. So which means that equation is in the form of p by q, and p by q is equal to root 3. Since we already know that root 3 is irrational number, if it is irrational number, it can never be you know classified as a p by q. It cannot be represented in the form of a p by q. Thus, a rational number cannot be equal to an irrational number, because 5q by p is rational, because it can be presented in the form of p by q, and hence it is a rational number. But our right side, which is the number which is we have, is irrational. So and hence, if it is a irrational number, then our assumption is that rational number cannot be equal to irrational number. So this is a rational number. 5 minus p is a rational, but root 3 is irrational. Since we already know that root 3 is irrational, and a rational number cannot be equal to irrational number, hence 5 minus root 3 is irrational number. This is important here, because we are not going to prove every time that root 3 is irrational by applying the method that we used in the example once. So we'll use that property instead. So likewise, we have an example show that root 3 minus 2 is irrational. So we will use the contradiction method here, that 3 root 2 is irrational number. Let us assume 3 root 2 is a rational number. We can present in the form of p by q, and then we'll divide both. So again, the logic here is that we have to isolate root 2. So which means that we have to maintain root 2 on the one side, and rest of the equation would be another side. So here we are saying that root 2 is equal to p by 3q. P by 3q is a rational number, but root 2 is irrational number, and hence they are contradicting itself, and hence 3 root 2 is a irrational number by contradiction. So we'll move to the next slide. Okay, now we will talk about the NCRT exercise. We have a set of questions. So exercise 1.2, we have to prove root 5 is irrational. So this is a specific case. So we know that square root of a prime number is always irrational, but here we have to prove it, and hence we have to prove it the way we proved the root 2 and root 3. We have to prove the root 5 as well. So this question can be proved with the help of the contradiction method. So let's assume that root 5 is rational number. So and it can be represented in the form of the a and b, which is p by q again here. So we'll solve it root 5 by b, root 5b is equal to a, and then squaring both the side. We have 5b square is equal to a square. So this means that 5 divides a square. So if 5 divides a square, then it also divides the a. This is the theorem that if a number divides a particular square of a number, then it also divides the number itself. Then we have to take a as a number, assume that a is equal to 5c, because this is a number which divides a square. So we'll take 5c instead of a, we'll put 5c, and then we are taking a square as 25c square. So which means that put the value of a square in the equation 1. So we have 5b square is equal to 25c square, and then b square is equal to 5c square. So which means that b square is divisible by 5, and so b is also divisible by 5. So this is largely the same method, same way that we have used the earlier equation as well. So we are just going to make sure that we are using the same logic here. By so in case of root 2 we have to take 2, in case of root 3 we have to take 3, and in case of root 5 we have to take 5. So we have to assume that in the root 2 case it is divisible by 2 in addition to the 1. In case of root 3 it is divisible by 3 in addition to 1, and in case of root 5 it is divisible by 5 in addition to 1. So in this case we prove that the a and b are having the common multiple as 5, so which means that they are not co-prime, and which means that they cannot be represented as a form of the rational number, and hence they has to be it has to be irrational. So therefore a and b have 5 as a common factor, but this contradicts that fact that a and b are co-prime. So this contradiction has arisen because our incurrent assumption and root 5 is irrational. So we conclude that root 5 is irrational. Now another example, we have to prove 3 plus 2 root 5 is irrational. So we have to prove 3 to is irrational. We will we solve this using the same contradiction method. So we have to solve the same way that we have used in the example as well. So for solution we have to move to the next slide. So 3 plus 2 root 5 is equal to a and a upon b. We'll again apply the same logic. We'll isolate root 5. When we isolate the root 5, we have root 5 is equal to a minus 3b upon 2b. And a minus 3b upon 2b is a rational number. But root 5 is irrational. We have proved above, or let's say we know this, that root of a prime number is always irrational. So hence root 5 is also root 5 is also a rational number, but this is the contradiction because root 5 is irrational. So therefore our assumption that 3 root 5 is rational, and hence 3 plus 2 root 5 is irrational. So prove that following are irrational: 1 by root 2, 7 by root 5, 6 plus root 2. So again we have to use the same logic, and at each logic we have to prove that because our root 2 is irrational, and hence our p by q can never be equal to root 2, and hence the number itself is irrational. Likewise for 7 by root 5, 7 root 5, we have to apply the same logic, and we have to prove that my p by q cannot be equal to root 5, and root 5 is irrational, and hence it cannot be equal to p by q. Likewise for 6 plus root 2 also, we have to apply the same logic, whereby we have to prove that p by q can never be equal to root 2 because p by q is rational and root 2 is irrational, and hence these numbers are irrational. So we'll move to the next slide. Okay, so with this we come to the end of this chapter, and we have also noted down some of the key points that we need to understand. We'll definitely come with more set of the questionnaires. We are first trying to solve all the NCRT's problem, and then we're going to look at other set of question. But point that we need to remember as a part of this chapter is that first is the fundamental theorem of the arithmetic. So that is very important here. And what does this state? That every composite number can be expressed as a product of the prime, and prime factorization is unique. Second, HCF is equal to product of the common primes, which is the smallest power, and LCM is equal to the product of the all prime, which is the highest power. HCF into LCM is equal to product of two numbers. This is another important concept. Prime factorization rule is always start with the smallest prime, write factor in the index form, maintain stepwise clarity. For irrational number, it cannot be written as a form of p by q. Decimal is non-terminating and non-repeating. Standard proof pattern is assume that number is irrational, write as a form of fraction, skewer and manipulate, show contradiction, and conclude it is irrational. Key concept for the board question is that use LCM when event repeat together. This is very, very important. This is in line with the question that we solved for that particular case wherein one person was driving to complete one round in 18 minutes, another was driving 10 minutes, and then we have to find at what point in time they will meet together. Use LCM when event repeat together. This is very, very important. Use SCF for grouping or dividing problem. So we have to use SCF for grouping or dividing problem. Ending with 0, number must have 2 and 5 as the factor. This is very, very important. What common mistake do students do is like wrong power in the factorization, mixing SCF and LCM rule, and then not reducing the fraction before checking the decimal nature. So with this, we come to the end of this chapter, and we're going to come with the next chapter very soon. Thank you for watching this video, and stay tuned with us. We are going to come with another chapter very soon.